I'm going to, I think, primarily focus on transferring a bit of information and some of the philosophical aspects of natural building and alternative building to you for the early bit of this, and then I really want to leave a lot of time for questions and how what I'm talking about can impact your designs directly. So I want to make sure that if I have an overarching goal, it's to kind of empower action in your design process on how you think about buildings. So that's kind of the hope. Anybody with building experience? Igloos.
Yes.
Snow forts.
Yes.
Yeah. Tree houses.
Yeah. Okay.
Sofa cushion forts.
Yeah, I got all that.
Creating spaces. Yeah. Good stuff. Okay. It all counts. You know,
Stick forts.
Was that stick building?
Stick forts, yeah.
Oh, yeah.
All the time.
Excellent.
You like rocks and sticks and put them across each other.
Mm-hmm. Tree huts.
Yeah.
It all counts. Anything you could comfortably get cozy in and spend a night counts as building. So whether it's in the middle of snow or whatever, it's So my background was I kind of stumbled into timber framing about 12 years ago and realized that it's something I wanted to learn a lot more about. Shelved it for a couple of years and ended up in the Southwest building with Cobb. Said, when I get back home, I am going to build my house just like this because it's very simple and wonderful, and didn't really have the understanding of this. And in the Southwest, there are certain building styles that make a lot of sense. In the Northeast, it's a more complex process to design, but it is very much possible, and it's more than possible. It's likely that you should be engaged in this kind of building, whether natural building or green building or whatever. But thinking about structures and shelters and the infrastructure associated with them in the Northeast climate is a wonderful, wonderful example of how to put your permaculture knowledge to use. So this is not a simple climate to design for. So, buildings. We ask them to do a lot. So, last couple of days have been anywhere from 92 to 104, depending on where you are in the state or how much direct sunlight you're in. 4 months ago at this point, we might have been waiting for 3 feet of snow to dump on us. A few more months, we'll be doing the same. We ask an absolute insane amount out of our buildings. And our finicky bodies tend to be comfortable in about a 5 to 7 degree range of temperature. So we also have this thing about not wanting to get wet while we're in bed sleeping, and we want comfort and durability and low maintenance out of our buildings so we can build them and then be somewhat separate from the process of maintaining them. So it's a lot to ask. So materials are going to be something we'll get into in a couple of minutes. So processes, design, standards and principles, and materials. Those are kind of like the three kind of overarching elements that kind of come into what I'm going to call natural building. It's a vague term, and don't have to use that one. It's kind of a specific format of building, but I think it goes really well with the permaculture philosophy, especially number one, observe and interact, because there's a lot of that when it comes to building. But as kind of hands-on designers in structures and infrastructure on your farm or landscape project, how you think about creating structures is no different whatsoever, and completely related to how you're thinking about your landscapes. And in particular with that, say, with the forest gardening kind of approach, which I really tend to think of buildings as their own ecosystem, and what are the inputs needed to make them function, what do they yield to you, and what kind of, where is that balance point between how much energy goes into the creation of a building to where does it start working for you, so what process or product is being yielded to you from this building. So that sounds a lot like needing a good set of goals to be articulated, it really is. And that's the design process really starts there. And I'm going to say, too, as each of you, how many weeks in or months in, how far along is this course? Like third or fourth weekend? Third weekend? So probably just starting to get, I'm sure all the ideas are fully percolated, and somewhere in here the waters are getting pretty muddy on what your designs are going to be. So if there's anything that you have, specific questions come up, just dive in with them. So we can stop and pause because I'm sure everybody will have some level of interest or something to gain from the question. So go for it when you got them. Okay, so setting goals. We set a lot on there, we put a lot on our buildings, but the function, aesthetics, adaptability, accessibility, budgets, timelines, things like that. So there's a lot of factors to consider. And I feel like, to me, kind of an important piece of how you think about your buildings and structures is how does the way it predominantly fits into our general culture, like this culture of the building industry. How are you as potential builders or people interacting with buildings creating a new culture around what buildings are? Right now there's a lot of very modular building materials. They're typically very processed, come from anywhere. Sometimes it's hard to even figure out where materials or products are coming from. And there tends to be a big separation between an end user and the person who took some bit of raw earth and turned it into something for use in a building. So plywood, for example, there's several levels of processing, and that's a rather simple one. A solar panel, there's an absolute ton that goes into creating that gets it to a building site. One of those happens to be pretty easy to replicate with native materials. A solar panel, we don't grow them here, but fabricating and the industrious process of making them can happen. But so something like plywood, how do you replace it? We live in a place, like our most abundant resource as a building material. One of them is wood. So plywood, very easy to eliminate. A step to a drive to a building supply store for a modular 4x8 sheet of plywood, something that we can create locally. Very simple example of how to rethink where what you're going to use comes from. So most materials that are modular, not all, but most, tend to be from some distance, manufactured in an energy-intensive way. So the goal is to rethink that, so changing the culture of the building industry, one building at a time. Okay, as we relate to the permaculture principles too, I think it's important. Every function should be supported by as many elements in the design as possible. Definitely goes for a building. So we can keep this away from being just a straight up throwing information at you. Let's get kind of a brainstorm going on what the building's functions are. So kind of popcorn style, we think of what do they do for us?
Shelter.
Yeah. And within that, temperature regulation.
Place for socialization.
What's that?
A place for socialization.
Yeah. That's excellent.
Yeah, George Carlin puts it, a way to put your shit. Place to put your shit.
That works. Yeah.
Position. Works against the wind.
Depending on the house, it could be a place to grow food.
Definitely. Yeah.
Place to cook food.
Place to cook
Yes.
food, there you go.
Good stuff. That's coming
A
up.
place to release your wastes inside, inner waste.
One method of doing that is playing nice outdoor methods as well.
Without methods as well, indeed.
An opportunity for creativity.
Yeah.
Opportunity for rainwater collection.
Yeah. Definitely. Capture. Yes.
Privacy,
Privacy.
security.
Yeah. Yeah. So that. Oh yeah. I don't want to stop it.
A containment,
Community.
a containment for babies.
Tell you, that's a big one in my life. Duct tape works good too. Hardly a natural building material.
Duct tape into the wall. Place to decorate.
Mm-hmm. I'd lump that with the opportunity for creativity.
Yeah, right, same category.
Yeah.
Store, create energy.
What's that?
Place to store and create energy.
Yes, definitely. That connects like that infrastructure piece of, it's multi-functionality. What not only sheltering and becoming a place for an occupant inside, but the outside of a building can certainly be used to capture things. Rainwater, sun, wind,
water, it could be windmill house.
water. Yep.
Or not windmill, what do you call them? Watermill.
Watermill, yeah. Yeah.
I think the concept of permanence or durability, and then disposal or reduction after its useful life is up, as opposed to something that's going to kind of hang around.
Yeah, it's kind of like compostability.
Yeah, something like that. Something like that.
That's
I
big.
mean, you want to be able to keep it going as long as you can, but then it's like, once it's reached its end, you don't want it to kind of be a burden to get rid of it if you're waste.
Yes.
Recyclable.
Recyclable, yeah. I had a few years ago, I worked on a project where I'd been doing this stuff for a while, and all of a sudden I realized not only had I never been on a job site or never led a job site that had a dumpster, and it had been pointed out to me by subcontractors coming and saying, "Where's the dumpster? What for?" Without even realizing it. All the leftover building materials, we had like sand, clay, straw, stone, timber. All these things either became something we burned or something we put in a garden or something we put in a toy box or sandbox. And I took home probably like 2 tons of leftover building materials from a project that all had other use, so no waste. In relation to minimal waste, there's usually something. Bale twines, I just can't use enough of those up to diminish my supply, but there's always something. But so limited waste, recyclability, compostability of materials. And kind of an overarching element to a lot of that, I think, is the healthiness of a material, and I think that's a very, very major factor. In a few minutes, I'm going to do my best to not launch into the overlap and discrepancies between natural building and green building yet, but 2 separate philosophical movements, but very related. But we'll get to it.
What about like buildings give a sense of place?
Mm-hmm.
Like I don't know. I have a lot of affection for just a building. It's been part of my life.
Yeah.
History.
Yeah.
Family
Yeah.
history.
Yeah. And I think of this aspect that the functional element of a building or the structure, insulation, and so on, and kind of like the cold functions tend to be very predominant in my mind as I go through designing buildings and dealing with engineers and regulations and codes. But there's this thing of, it hit me a few years ago where if you don't love something, you're never going to take care of it. And the beauty or the history or like that, the intangibles of how you relate with the space is, we've all had those experiences, whether it's a sofa cushion fort or a 300-year-old barn that somebody's grandfather owned. You walked in and just felt it. It's as designers, it's what we're after. And it's a very selfless act to work towards that, because you're really thinking 7 generations or more of what is this that's being built, and how do we do it in a way where it's always going to be loved, taken care of. And ecologically speaking, I don't know if there's a more noble goal for a building than make it something everybody's going to want to be a part of. And in Japan, for example, a lot of my more official practice has been in timber framing. I've gotten to work with timber framers from Japan who, there's these 4 levels of design, and that you kind of move up towards like absolute master craftsmen. There's very few, a couple dozen in Japan, but level 1 is building homes. That's like anybody kind of can do it. And second tier is community spaces, non-religious community spaces like schools or institutions or whatever sort, like larger community function buildings. Number 3 is temples. I always kind of thought, temple builder, that must be the pinnacle of it all. But any guesses at what the highest standard?
The garden.
Close.
Restaurant.
Tea house.
Tea house.
Yeah, the garden tea structure. That's the final tier of the master builder in Japan from a woodworking point of view. And the reason is, for one, it lives outside. It's an open air environment, and it's supposed to be that perfect relationship between indoor and outdoor spaces. And so
So it makes me think about light and sound, sort of shelter, but also access.
Yeah.
So
Important component.
the building provides a connection to nature, sort of?
Yeah.
It should be part of nature. So I always tell my mom, she's always complaining about bugs in the house and mice and stuff. I'm like, hey, this house was put in their property. They're part of this environment. It's deal with it.
So it's the access, and then it's the shelter from the guy across the street who keeps shooting his gun and making a lot of noise. So there are both of those components.
It's a very breathable wall. It's a big movement in natural building, or it's kind of an outdated concept, like the breathable wall, that lets air in and out. And the walls works pretty well.
What about just the functionality of the buildings to give us like a sense of like the locality of culture? You know what I mean? Like a local vernacular.
Yeah.
Just identity, maybe, or some such.
Yeah. There are certain building styles in New England that, to me, I've done a bit of traveling, not nearly as much as I would have liked to, and maybe will at some point, but enough to know that the New England building tradition is so special. And it's kind of unbelievable, because from a timber framing point of view, there's 11 principal styles of joinery out there, and New England was the absolute melting pot of that. So through colonization and early centuries of advanced building techniques here, and a lot of the buildings that are still standing, there's like 11 distinct cultural traditions that kind of came to place here. And it's fantastic. I mean, somebody should write a natural history guide on New England barns. I swear it'd be a fun read, but geeky read, but fun read. But New England is an extremely special place with their salt boxes and colonials and capes and the high-posted cape design houses. These things are so efficient, and people keep coming back to them now more and more. I mean, there's fun elements we can add and alter from these traditional building approaches, but there's a New England farmhouse. What a selling point that is to a person that can just feel that 250-year-old tradition. As a builder, I very much wanted to build my own house. That's why I got into building, and then ended up buying a 266-year-old house. And I love it.
Yeah.
It's about inefficient, pathetic as it can be.
Exactly. Yeah. When we, I bought a 200, or it was built about 1787, the farmhouse that I live in. And when just the first visit with a real estate agent, I walked into the barn that was about to collapse. And I stood in there for like 5 minutes and was like, I'm going to die here.
Yeah.
I'm going to be buried. I just knew right then I wanted to spend the rest of my life there.
Yeah. It's great. So that cultural tradition is huge, and that our connection to the past and our segue into reskilling for the future, I think, is huge. The idea of a place to get together, those community functions. I'm just not going to do it in a suburb built in 1982, that's for sure. I'm not going to feel the same way on a vinyl floor, like an old wide plank floor or something. It's huge. And when you're in a space and feel its history, and feel its imperfections,
Those
and
old
just
Victorian rooms and stuff.
What's that?
The old Victorian homes you see in certain places, like the cities.
Mm-hmm.
Those things are beautiful.
Yeah.
Like up in Newton, that's
Very
right up in
fancy,
Newton, Mass.
fancy architecture.
Yeah.
Yeah.
Looks like
Yeah, the
castles.
status symbol style of
Like
you know,
spires and stuff.
Yeah,
Like little like Disney princess castles and things.
yeah. All right, so I'll try to stay on task. So this is at least a 2-day bunch of info that if there's a certain kind of buzz phrase I say or bumper sticker slogan that resonates, ask a question because there's probably 45 minutes behind it. I've got all my just keynotes, so I'll buzz through some of them just to understand. The idea is not to be thorough on natural building, but that was a bit of the overview of what we're after. You know, changing the culture of the building industry is fundamental as designers, just the same way, you know, as permaculture enthusiasts, changing the culture of lawn. You know, that's really the same thing that we're trying to do. So I'm going to skip over a little bit of stuff and just quickly say energy efficiency. It's a big buzz phrase these days on building tighter buildings, and there's a ton of value to that, and we'll get into it a little bit more. But behind, I think what natural building has to offer is a chance to look at energy efficiency beyond just fuel or fuel use or consumption, but the human energy that goes into the creation, both localized and globalized human labor. So modular materials could be made anywhere. Unhealthy building materials can be produced far overseas, and it's like the sweatshop style of building material production for our use. And it's a direct and fundamental aspect of natural building is to question and eliminate that kind of outsourcing of production and relocalize. So looking at human energy efficiency and mechanical energy too, so that embodied energy piece. But really after keeping it close to home, and that is, you know, the challenge here is to find, or I'd say the problem is the solution, because we're limited in the Northeast. And I'll tie into some more technical stuff here in a moment, but where our climate is 110 degree fluctuations, you know, or more with wind chills, it's ridiculous how much variety and, you know, of what we've got for weather and in our material use. So here in New Hampshire, Josh can tell you just as much. It's really frustrating. One of the predominant natural building materials that we'd like to have a lot of access to is clay. New Hampshire, man. The same for Vermont, where there's a lot. So it's like working with what we got and how far is local. It's this big movement of the 100-mile house right now, and people all over different climates throughout the world, from Mongolia to Vancouver to Vermont, are designing the 100-mile house. You know, every single thing coming from within a 100-mile radius. And New Hampshire, it's like we got a shot at, you know, crossing over that river and grabbing some Vermont clay, but you know it's tricky. So yeah, we've been working on, as a group of us, been working on trying to do that, and probably not going to pull it off yet. But, so Baker River's plenty of clay, but we're not supposed to take it. So that's the energy efficiency bit. Site evaluation, I'm guessing we've gone over that quite a bit already, or is that kind of to
Just
come?
going to be going into design, the whole design weekend in August.
Okay.
So like evaluation, the analysis and assessment, all that, they haven't
Coming
done
in.
yet.
Okay, all right. So I'm not going to get too much into it just because it's going to be covered, and say the caveats to me not going into it are there's a couple of specific building related aspects. So say solar and wind exposure. This could be for a building or a plant in some cases, but right now I think buildings. Passive heating and cooling strategies. Food growing and farming potential. These are all aspects of where to put a building. This is a very quick snapshot.
The site analysis, right?
Yeah. Designing for changing family sizes and needs and adaptability through age. Designing for climate change. It's a 2-day workshop right there. Summed up in 5 seconds. How's that? and the role of the building, knowing that the purpose and maintenance schedules and so on are going to be kind of fundamental. And so the purpose will change, and the maintenance schedules are going to be unpredictable at worst and regularly scheduled intervals at best, but maintenance. So, important things to consider while designing a building, or while siting a building, I should say. And when designing a building, we'd add just a few more things. I do want to launch into materials here in a moment, but I'm sorry it's brief. One other aspect when it's, I think, a good connection to the permaculture design philosophy is designing a building with microclimates in mind, and thinking about your building again as an ecosystem. You create the microclimate of a south-faced bedroom wall versus what you would do on the north, or space heating and cooling in room-by-room aspects, and knowing your own habits and functions and how you're what your lifestyle is going to be. So, for example, the typical 9-to-5 kind of job is one very distinct way to use a building, where you need heat, water, electricity in the morning, and maybe the space is vacant for many hours during the day, or mostly vacant, and then in the evening you need your heat, water, electricity again. Maybe, if you work from home, you got one room that's really important to keep warmer or cooler or darker or whatever it is based on your own lifestyle and schedule. And designing your food, interior food growing, processing, storing capabilities and needs, in your space. And that's a lot beyond kitchen design. It's very much beyond that realm of really thinking like what your food habits are, your family's food habits are. So it's doing your kind of personal observing of lifestyle and really kind of taking into account how to best build a building for your needs, making it adaptable to other people's needs and your needs as you age, and keeping in mind that you don't need, very much can question the concept of I'm building a timber frame straw bale house and making all 4 walls, or making it a rectangle at all, and then all 4 walls are going to be the same, and each room is going to have like the same materials, and you have an opportunity, a challenge and an opportunity to say, I want to make this as custom to my needs as possible. So from your lighting to your heat and cooling needs, absolutely, but also your warmth needs, your aesthetic needs, that are your intrinsic space requirements and needs. So a lot of people customize the interior of their houses with colors through painting or through decoration or furniture, or the application of something personal to a wall space. But if you make that building itself your expression, you're taking it kind of one step further into designing something unique, beautiful, you're going to love and take care of. So. Any questions yet?
Just one thing I'm thinking about, like, I'm almost 60, so I sort of know what I need right now. Mm-hmm. But when I first started building my house, I just really didn't have a bigger picture of, like, kids and all that other stuff. So some of us are just going to make mistakes as we go along, and that's going to be the lesson, that we create something eventually that maybe will meet somebody else's needs to begin with. But you can only do what you have access to. Like 30 years ago, 3.5 inches of pink insulation is what they said was what you needed for your walls.
Yeah.
25 years later, I'm tearing off the sides of the house and adding on another 6 inches to make 10 inches of dense packed cellulose. But it's kind of, it's great to be, this idea that's happening now. People are really getting the opportunity to learn from each other's mistakes and learning resources now. But I think there's probably, even in your case, you'll find that you'll do things and later on you'll learn, oh, if I had done that.
Yeah. Yeah. There is no project that
Right?
I've ever completed where I said I would do it just like that again.
Yeah, it's
Never. Whether building or otherwise. Yep, absolutely. Absolutely. And yeah, to learn from mistakes concept. Big. Yeah. All right, so I'd like to just talk through a few pieces a little bit more concrete. I hesitated trying to come up with another word because the first one we talked about is foundation. So, yeah, that's why the C word kept jumping in mind. More tangible. So that's what I was looking for. So thinking about designing, so that's most of the general background stuff on what you're after, and then the actual house design. And I'm using house too, knowing it could be a barn, it could be animal housing, it could be a shed, it could be a greenhouse, whatever it is, whatever kind of structure. But the house is kind of the most complex, so take it from there. And if your own design calls for a barn, you get to simplify down like crazy. So this whole concept of insulation and energy efficiency and so on. If your building does not call for that, you can tune me out. But house is the most complex, so I'll talk about that and then just whittle it down to what you need. But foundation, number one. So conventional foundation, I distinguish between saying conventional and traditional too. They go back and forth a lot, but traditionally everything was natural building. Everything. There was no alternative. And somewhere in there, depending on your own standard or understanding of the history of building, that switched, and balloon framing became a popular thing, which is kind of framing up two walls at once, the first story, second story, continuous pieces of milled lumber, and that lends itself to modular building materials, like late 1800s, early 1900s, kind of a movement towards that. So whenever that line in the sand was drawn, it doesn't necessarily matter, but traditional building is natural building. Conventional building we use as a term of the modular approach that has plenty of advantages to it and the simplicity and so on, but you can get that anywhere. So foundations, conventional foundations would typically have, for a house would have 8 inches or so of poured concrete down all the way to like a frost line, which here is, depending on what part of New Hampshire, 48 to 60 inches deep. So down under grade level, 48 to 60 inches, there's some sort of concrete footer. There's a big wide bit of concrete that is below anything that can move with freezing temperatures and heave and move around on you and just create havoc down the line. So we've got concrete in some form or another, whether it's up here or a wall coming from deep underground up to the surface and kind of wrapping the perimeter of the house. Just say for now like our rectangles, 24 by 36, 8-inch thick, 4 to 5 feet down. I don't know what the volume of that is, but it's a whole bunch of concrete. Concrete's one of those materials that has, I think, a time and a place for sure. It's Portland cement in particular, extremely high on embodied energy, but it's extremely strong with compressive forces, like downward forces. So you can set a house on it and it's not going to move. You can put a lot more than a house on cement in a direct downward compressive force, and it's going to withstand that for a long time. It's a different story if it's unsupported. Say with a 12-foot span, you put a big weight right in the middle, it's going to crack relatively easily. So you need a lot of mass in order to kind of use it effectively when setting a house on it. So conventional building now has 16-inch on center stud frames, 2x4 or usually 2x6, either wood or steel studs come down. And so that's one way to, you spread a load across an entire perimeter or entire wall surface. And in a timber frame structure, has a lot of advantages to minimize concrete use, because you've got, say, every 16 feet, you've got an 8x8 post coming down, and a load carrying beam of some sort at the top of that. So you've got weight coming down every 16 feet or thereabouts. So you might have like 8 to 14 of them in a building. So under each of those, you need some sort of concrete or connection to stone or bedrock or something. And you get to eliminate just about all the other concrete in that wall surface. So if you have a basement, then there's other advantages to having a wall, but it's not always needed. A lot of times not recommended, especially when we get into food storage and root cellaring. There's a lot of advantages to not having a concrete wall as part of that. So foundation is pretty big. Walls, I think, are kind of self-explanatory in what they are, but they can be made up of 1 trillion different materials. So in natural building, there's about 6 predominant wall systems. And that would be, there's the dense packed cellulose was mentioned, and that's kind of on the periphery in the natural building world. I think it's completely warranted to be in the discussion of it. It's usually recycled newspaper treated with borax or borate and sprayed or blown into a wall cavity and provides really good insulation. There's using straw bales, which we'll get into some photos and talk about wall systems.
Sorry, can I ask you a question?
Absolutely.
We went back to the natural with the timber.
Mm-hmm.
You were saying you were 16 feet spans with the vertical timber? Every 16 feet?
Yes.
Each
yeah.
post, yeah.
So there'd be a post every 16 feet, usually some sort of bracing, a lot of different ways to do that, and then some sort of horizontal beam at the top that would carry a second story load or a roof load. So it's called a point-loaded foundation system, where you've got usually 8 to 14 posts, or depending on a barn, would have a lot more, but the entire weight of the building and all the building materials, occupants, and furniture and so on bears down in just 8 to 14 spots.
Yeah, then when you were relating that to the foundation, that's where you would need a full foundation?
Right. Exactly. Yeah, depending on your overall design, and sometimes there's benefits to having a wall, full wall there. A lot of these wall systems end up having their own needs for a foundation, and they're usually simplified. So I'll show some photos. There's straw bale and straw clay and wood chip clay and cellulose and all sorts of. So there's a straw bale wall, and by straw, to distinguish between straw bale and straw clay. A straw bale uses an entire, somewhat modular material of the straw bale, which is typically 14 inches wide. It's called 2-string and 3-string bale, so there's different standardized sizes for straw bales, but usually, 18 inches wide, 14 inches high, and anywhere from 32 to 40 inches long. And they're very imperfect. They come, roughly that. So a straw bale can either be laid down flat, so it's 18 inches wide, or up on edge where it's 14 inches wide. They actually insulate almost identically between those two because of the way that the fibers run in straw. But it provides a very high R value. But a bale is not very heavy, but relatively heavy. So an entire wall, say this kind of gable wall there, that's probably like 36 or 3,800 pounds of straw. So that needs to bear down on something. A timber frame can do it. This particular building, there's a timber frame on the inside, and the straw bale is a pretty common approach now. Wraps fully around the outside, so the frame is completely interior, and then the bale system is completely exterior and unbroken. So there's no air infiltration outside to inside.
It's kind of like sips with straw bale.
Yeah,
sort of, right?
Yeah, this is the anti-sip.
Right.
So do they not cover the outside with anything?
What's that?
Do they cover the outside of the straw bale house with anything?
Yeah. Plaster. In this case, we can use plaster or wood siding, or in the southwest, there's the inside of the same space. Right there, plaster. That's what this particular mix is a very common plaster recipe for our northeast exterior climate would be a minimal amount of lime, so like about 1 part lime to 1 part clay to 3 parts sand. And so sand is the strength of a plaster, and we have lots of that around here. Clay, depending on where you are, it's hit or miss if you've got clay. Globally speaking, it's an extremely common, predominantly easy to find material, but our little nook here, not so much.
Can you say that again? 1 part lime? No.
Yeah.
1 part
Yeah.
lime, 1 part sand, and 1 part clay.
3 parts.
3 parts sand.
3 parts sand and 1 part clay.
And 1 part clay.
Okay.
Yeah, 1 to 3.
What kind of R value?
3 parts
Brian?
sand.
On a straw bale, so typically with a straw bale or any of these other kind of natural wall systems, there's an interior and exterior coat of plaster that acts as an air seal, and there's some detailing on how to connect it to a timber frame. So I'm skirting around that question, but I will get to it. So
Okay.
R value, does everybody understand, or people have heard that phrase? What the R value is measured in how many British thermal units of heat leave a space and enough to sufficiently drop 1 degree over a 1 hour period of time. I think that's right, but the concept is how much heat leaves a building. So how good is a wall or a material of whatever sort at keeping heat to the inside of a space. It's an extremely hard thing to calculate. It's extremely easy to do in a laboratory on a material by material basis. It's a lot trickier to think of how an entire system works. So it'd be kind of like saying, if your yield in a garden is fruit, you can measure just how much fruit you've got. And it's not telling you what kind of beneficial insects have occurred and what kind of soil building has occurred. It's like these hard to measure things. So it's one way to measure how a wall system works is material by material, taking the R value and adding them together. And it's by inch usually, like how many inches of this material will do this. So to measure the entire wall system is where your benefit is just huge. It's dramatic. The simple answer is about an R32 for a straw bale when plastered inside and outside. And the plaster acts as an air seal, which means it blocks air infiltration. And it's called a stress skin. You mentioned the panel. So structural insulated panels are this thing, and they're sometimes called stress skin panels that kind of wrap around a building. There's like a sheet of oriented strand board, and then a bunch of rigid foam, and then some more oriented strand board. And it works as like the sandwich system where it's extremely strong, where it's like, and it acts to insulate if it was just heat going back and forth, but it also adds a lot of rigidity. It's like adding sheathing, insulation, and sheathing all together, where it just makes this really strong thing. So it keeps a building from like racking. So put a frame up and put a panel on one side, the building is probably going to blow over. If you put them up on all 4 sides, it works as this very strong unit. Plaster on a straw bale is the exact same thing. It creates like a stress skin panel of plaster, bale, plaster. And when all those things kind of work in conjunction, it's an extremely dense and efficient wall insulator and air barrier. So, it's a very excellent method. I think there's another question in there, or today.
I stopped.
Okay.
Am I going to get ahead by asking about maintenance?
Yeah.
Okay,
Yeah.
I won't ask you.
Okay. Okay, so the wall systems are straw bale. It's that modular approach, and straw clay is another one when you actually just break the bales apart into loose straw and mix it with clay. I know there's something here. So here's just a finished plaster look, a real simple one. You guys are going to be working with this outside, so I'm not going to get too much into working with it, but you'll be doing this on the oven outside, which is great. Plaster, lots of work, recipes. I do want to this is a straw clay building, so testing out different plaster recipes on trying to find the best one. But so the straw is just broken down and mixed with clay in a very heavy clay content, and then it's plastered on both sides. But a huge benefit to that is you can make that wall. It doesn't have to be 14 or 18 inches thick, and you can make it 8 inches, 10 inches, 12 inches. Those are kind of common numbers. 12 is the most common, just to maximize your efficiency. But because it's mixed with clay in a very wet form, you have to. And our climate is tricky because you have to let it dry before plastering it, and that can take usually about 3 months. So it works with the overall process, but it's tricky for folks who want walls up and move on to finished carpentry in a quick way. But yeah. So actually, this is I think a pretty good example though. This foundation, there's concrete footers underneath, and there actually are a couple walls of concrete to a full finished basement, but then there's a lot of field stone built up, a full stone foundation on several sides, which is great. You know, it was all came from the excavation process and on the farm where this building was. So local material. So foundation, that's a good foundation to wall detail. It's just stone to straw. Concept of moisture wicking, is that probably familiar to anybody who does any hiking? That's what I remember first hearing about, you know, the benefits of synthetics, was how moisture will wick away from your skin. So, natural cotton versus polypro outerwear. Wicking in a building is a tremendously important concept. So concrete with its cement content will actually wick moisture up. And water is, in most cases, kind of detrimental to building materials that have, to natural building materials in general. So you want to keep them dry. So a foundation, you'll notice this comes up pretty high, almost waist height here, to keep the straw up off of the ground. Is a really important aspect of things. So both for heavy snow, months and months of snow buildup and being saturated under all that ice. And also just for moisture wicking, it's big. This happens to be a stone foundation, so this is just for snow. You could have the straw, if we didn't have snow build up, just a couple inches up. Concrete will wick moisture up, so moisture will hit it and just kind of go up, and rise vertically and then get into a wall system. Mm-hmm. Tremendously detrimental to anybody who's had termite problems, mold problems, mildew, anything like that.
The garage is like crumbling from the ceiling down. Yeah. The concrete kind of gets all crispy and just turns into dust and falls off the walls, like the paint and everything. Yeah. And I think it's probably just gets really moist in there. It's flooded through the top before. Huh. Yeah. It's like an underground garage, sort of. Like the back of the house is it's like the house is on a hill, so the backyard is above the garage, so all the water comes from the backyard into the roof of the garage, and then soaks in, and it's all degrading that way. Yeah.
Yeah. So water is kind of, pretty fundamental to our bodies and our lives, and pretty much the enemy of buildings. So conventional or not, most materials will break down in some way based on different forms of water, or vapor, or liquid.
So in this picture, you're saying that the bottom 3 feet or whatever that bottom is made out of what? Stone? I can't see.
It is, yeah.
It's made out of stone?
Yeah. Stone found in sight.
And so that won't wick anything up to...
No. So, but an interesting thing here, though, is there is some concrete in the mortar holding the stones together, so there is some moisture wicking that could happen, but not enough to be. That's a straight high
rocks or whatever.
Yeah. So it probably wouldn't be much of a concern, but it could be. But so the foundation, it's one way to do it is to just put your concrete in just where you need it, and then just where your load is actually coming down, or all the weight's coming down compressively, and then do something else throughout, and that's what this is doing. It's more or less just holding the straw.
And actually, I'm trying to think, I remember seeing somebody put a sheet of rubber or something like that.
The tires.
Defining something to separate it from the bales. so that the bales, so that nothing could go.
Yeah.
Is that
It's
a
pretty
practice?
common. I've never seen rubber, but it would work.
What's the substance that you've seen?
There's a couple of different ways. Sometimes, from an insulation point of view, you can actually use, like, I think it's one of a few appropriate uses of rigid foam, which you can usually get reclaimed. Or you don't always have to buy it new. But foam, because it does insulate pretty well, it makes a decent barrier. But you can also use, depending on what your insulation needs are and your overall building strategies and goals are, insulation and energy efficiency and air infiltration are huge, huge concepts. And depending on what the need for the space is will determine what materials chosen and what you have available, hopefully, too. But yeah, there's a lot of ways to do it. A lot of times what we do is we put two 2x4s. Yeah, so if you're working with, say, a 12-inch thick wall like this one, two 2x4s down on top of the stone, and you can use that to shim up and level to make sure that that gets perfect. And then on the inside, you spray in either dense packed cellulose or just fill with gravel. If in a straw clay unit, I would use gravel. In a straw bale where there's no moisture in the bale when you start, you could use a strip of rigid foam, like 4-inch wide piece of foam, or the cellulose. And the reason you'd want the gravel in this is when you do a straw clay mix, there's a lot of water in there, and that clay is masterful. There's nothing that could be synthesized to better deal with moisture than natural clay. And water will go in and out of it, and it will hold it. It can take on so much weight like a sponge and then diffuse it through back to the air, and clay is amazing. So the straw clay building system is made to accept the fact that there's a lot of water in the air and it can infiltrate through. And the straw makes it pretty airtight, especially with the plaster, which has a lot of clay. So you've got clay, then clay in the walls, then clay in the plaster. So water, vapor can mitigate its way through very well, but air won't get through the plaster skins, the interior and exterior plaster. So it's a phenomenal method just for that. But because you're putting literally thousands and thousands of pounds of water mixed with clay in, when you build the wall system, you need to account for some of that settling. Most of it should dry through the air, but some is going to settle. So you put 2x4s, called a toe-up detail. You put 2x4s down and fill it with gravel at a slight tilt where it's going to export it to the outside of the building and drain out. And it will take like the first year for all that water to drain out.
And in that process, you can even see sprouts and things like that happening in the...
So you can, a lot of times, in a straw clay system, when the wall will sprout, and when it dies, that means there's not enough moisture for any life, and it's safe to plaster. It's the number one way to dictate to you when it's ready. So, big bumper sticker slogan here, natural building. It's working with natural functions, systems, and seasons, and not against them. So you can't force when plastering is going to be ready.
That's why it takes 6 months for the hay to dry itself.
Yeah, no hay.
Straw.
Yeah, there's hay in the system that doesn't work because the seed head is there and it's pretty tasty for insects. So this is straw.
So Brian, if we could just take sort of a basic review right here. We've gone over the foundation. The foundation is, got to be solid to bear the weight. It can't be permeable to moisture. You don't want moisture wicking up into the building. It's got to resist the freeze and thaw that we have to deal with. And then now we're into sort of the envelope.
Yes.
And dealing with insulation. And insulation is can be quantified with this R value, but we've also got to look at the bigger picture where we're dealing with draft. And you can build a really nice refrigerator, but if you leave the door open, it's not going to be efficient. So you're really looking at the whole envelope idea. And when we get into this envelope idea, it's a seasonal difference that we're really trying to accommodate. We're sometimes in the spring we're fighting rain, trying to penetrate the building. And then in the winter, we're fighting a whole different beast. It's the beast of when you have an interior heated space, it's pushing moisture out. So the walls have to be able to allow moisture to pass through them because of this very dramatic seasonal difference. And then when we get into this, what Brian's been touching on is it a vapor barrier that prevents the flow of air, or is it a moisture barrier that prevents the flow of moisture? Because if you get into a moisture barrier, you're going to get into a situation where you have condensation on one side or the other. So it's sort of slightly different things. An air barrier is going to be slightly different than a moisture barrier. Different purposes, different sort of reactions to these pressures, environmental pressures.
Those are important differences. So I'm still struggling with what to do, how to insulate our 200-year-old house with the walls, and where to put the vapor barrier and moisture barrier. I'm still struggling with exactly how to do that, because it's how they did it 200 years ago and how they purposefully designed it that way.
Yeah.
And the modern technique, which is so radically different, and I don't know which way to go. Every time I talk to a different contractor, I get a different answer, and they always say the other guy's wrong.
Sure. There's one of the books going around here is called, nope, not even that. It's The Little House for a Small Planet. Yeah. That one really touches on a lot of renovation, which I think is the future, the biggest single avenue for natural building. I'm convinced that for us with old houses, I mean, it's just what
There's just so many houses out there, it has to have be done.
Yeah, in new construction, it's awesome, and it's the goal as a builder, because it's really fun to get to do it. But it's renovation. That's where it's needed. That's where the most people are going to be impacted by the health benefits, the legality of materials. But yeah, air and vapor and moisture barriers are different things, and sometimes vapor and moisture gets lumped into the same category. So a typical system people have probably seen is putting Tyvek up on a house, or some sort of house wrap. And boy, that's a great air barrier. Like when a conventional wall would be like a 2x6 stud filled with fiberglass, or more often the case now, so I don't know anyone who build with fiberglass anymore, but some sort of insulation in between them. Sometimes there's 1 inch of we're gonna hold on, let me hold that thought, but we'll get into right there, thermal bridging. So this Tyvek concept of, so you've got stud frames. Oh yeah, you can't see where I'm pointing on this again.
You use a mouse on the screen.
Pretty common, interior, exterior stud, 16 or 24 inches on the center, filled with insulation here, and then out there just plywood, which is or 1 inch sheathing boards, which it's a localized, a very simple step. But whatever it is, you've got sheathing. Usually it's drywall on the inside, which is what's called your interior. This is conventional buildings. It doesn't have to happen, but your interior air barrier. Ideally, you have an interior and an exterior air barrier. And it's literally makes it close to impossible for air to go from one to the other. And the biggest, as Josh was saying, like the concept behind that is like the pressure differentials. So inside to outside, where you've got this warm air, conditioned air, and some level of moisture content. And then outside, you've got like sun going up and down, and this variation of minute by minute and hour to hour variation. Not to mention days, weeks, seasons, but crazy amounts of differences in our finicky bodies wanting almost the same thing year round on the inside. So we've got this pressure differential constantly occurring inside the wall that creates a dew point somewhere. So if you have an interior air barrier of drywall, which is gypsum board is a great natural material when it's not just modularized into these sheets and treated with fire retardants and so on, and made to be less healthy than it is on its own. We've got an interior air barrier, insulation, and an exterior sheathing, and then usually exterior air barrier. And a lot of times that would be Tyvek or whatever kind of house wrap.
What is Tyvek?
Tyvek, it's a poly. All these chemicals.
It's the same thing. I think it's dental
So
floss.
some sort of
It's the
this might be this.
what is the kind of dental floss? The
This might be Tyvek.
yeah. It's like
The special
there's
credits.
You like can't.
Glide
It's a
is.
plastic
I
sheet.
mean,
It's
but it's
Figured it
thin.
out.
It's
This is
yeah,
done.
which one?
Sure.
I thought,
64th of an inch
You like
thick.
can't rip it.
It's a roll. And
And
there's different ways, different things. You don't have to use a house strap, but
Yeah.
it's really common and it traps. It does a pretty darn good job. It's 3 foot and 9 foot rolls, and then you tape the seams, and it does a pretty good job of trapping air to the outside, so wind can't penetrate into your wall system as easily. It will still get through, but not as much. But then you got this. It will allow some vapor out, but condensation happens. So inside, if your interior air barrier is not perfectly sealed, which with gypsum board or sheetrock, it's probably not perfectly sealed, even when it's painted and everything. Moisture or vapor is going to get into your wall system, hit that tie back, condense, and turn to mold. And 1950 to 1998 or 2000 or something, that's what happened all over the place. And so mold and mildew and health issues started arising. Yeah, I'd love to get into the healthy aspects of things, but I want to talk about some of these forces first. So thermal bridging is huge. This is it's a really important concept to grasp. So a lot of times these studs and things are nailed. Wood is a horrible insulator. Well, it's actually not horrible. There's worse, but it's a very poor insulator. So this wall system is usually a 2x6 is actually 5.5 inches thick. So this is about even if you've got that filled with the best insulation in the world, so there might be an R40 right here with some super crazy spray foam, disgusting material. R40 right here, and then this wood is an R5. An R40, R5, an R40, R5, and so on. So your wall as a whole, as a system, as a unit, decreases in efficiency drastically. We're not even talking about sticking windows that make holes in yet, but it's just, it drastically decreases your wall's thermal performance. So there's all sorts of other ways. So in a straw bale or straw clay, this other thing called wood chip clay, we'll touch on. All of these types of systems have no thermal bridges, which is just, I think that's kind of self-explanatory what it is. It's like the material that is, conductively lose heat constantly. When we break that up and this does not touch this, your air barrier or your finish, whatever it is, has...
It's just going into rest.
Okay. You don't touch it long enough, huh? It shouldn't be the battery. So,
I think we could really see this on this building, because we have a really good insulation product in the wall cavities. But if you look on the back side of the building in the morning when the dew is setting, you can actually see the studs.
Yeah.
Yeah, because of the condensation and the different, it's the dew point that's happening on the outside of the building.
yeah.
So it's very apparent. This is the conduction of building materials really is in relation to the R value, so to speak. You have something with a high R value and it's got something hot on the other side, you can't feel the heat. You have very conductive material like metal, will come right through it. So the R value is its capacity to resist that transfer of heat, that thermodynamics.
And this gets into that, but I think Josh just summed it up pretty well. We'll skip it. No, that's perfect.
Brian, will you staggered those studs?
Mm-hmm.
In between is the straw, is that what we're talking about? Or?
Excuse me?
Straw.
Or cellulose, or...
Oh, yeah, whatever your insulation is. In a second, I'll show a chart. I think it's right after this one, different options and how they work. We'll talk about thermal mass in just a moment. But, this is... maybe we can even kind of skip that, but yeah, we won't get into windows yet.
I think for your question already, you can put loose fill in there. It's just it's less applicable for say the standardized pink insulation that'll go in a 16-inch cavity.
Yeah.
So, but it's more applicable for loose fill. Like if you do loose fill cellulose or something, then it'll be able to weave through there and give you that prevent the bridge.
Okay.
Is the idea. is to just have a continuous envelope that doesn't allow that bridging, that quick escape, that draft point.
How do you actually build that? With a conventional wall, it's one unit all nailed together.
You build like a 2x6 plate on the top and the bottom,
Yeah.
and then put 2x4 studs in, offset.
Do it 2x6 plates.
Alright.
So your
Okay.
plates
So
are
the plate's thicker than the studs.
Yeah.
Right.
And if you're using native material from the mill, you can order like whatever you want your wall thickness to be. You can make it in a different way. Look, there's a lot of fun ways.
And lots
to
of
get
this
creative.
too, in the timber frame construction, these wall systems aren't necessarily bearing. So you can use
Right.
a 1.5 by 1.5 stock, or that's pitching it, but
Yeah.
you can use a smaller stock and offset it and actually use less wood to sheathe to provide the sheathing surface.
Okay.
So it's not necessarily a load bearing function at this point.
Yeah.
Okay, I get it.
Just holding up your
That's what confused me.
insulation.
Yeah,
But it makes
What's
the
the matter with
lighting
that?
breeze.
Does. Yeah.
What I missed was changing that 2x6 plate
Okay. Yeah.
until we just thought it through. Okay.
This is just a quick graph on thermal mass is a concept of, this is probably out of order, I'll go down one first. Okay, so here's the insulation, the mass, thermal mass continuum it's a really important concept on like the whole wall system, the whole performance system taking, like performing together. And insulation is anything that kind of traps heat to one side or the other, or cool out or whatever. It has that kind of purpose of preventing heat flow. And mass is something that a thermal mass concept is anything that kind of takes up, stores heat or coolness, and slowly disperses it back over time. So, like a stone patio, 2 hours after the sun goes down, you go out on it barefoot, and the rest of your body might be getting a little chilled if the night's getting cooler, and then your feet feel perfect. And it's this whole concept of tile and stone and so on, like these materials that kind of capture the heat during the day, slowly radiate it back, and also stay cooler longer into the morning. So how do you work with that kind of concept? And this is where truly like the renovation world of natural building has so far to go, and it's really exciting that it's clearly going to be the dominant cultural norm within 30 years because it simply makes sense and has to be. But thermal mass, integrating that into every space is kind of like your space heating and cooling strategies. So a lot of these materials, do these sound sand and clay? We talked about those for plaster, right? Mm-hmm. So these are excellent at thermal mass, depending on your thickness and the actual mass, like how much of something. But the concept of a masonry heater works like this, or even a wood stove to an extent. But so you heat it up, and then very slowly it's going to give off its heat over time. This is a good breakdown on like the most common wall system. So straw bale is way over here, and it's definitely the best insulator of the group. It will do a pretty phenomenal job of, acting, as we were saying, it's like an R, roughly 30, 32 or something like that. Boom, that's great. The conventional fiberglass wall, when in performance, is R7. It's listed as R13 between the studs on 2x4, R19 on 2x6, but when you put it together, it's either R7 or R10. Pretty pitiful, it's a horrible performer. Cellulose works better. All these different things kind of work out. Spray foam is out there now as a very predominant choice. It works pretty well as long as value your lungs. There's all sorts of problems with it, but straw over here, very good insulator. Cob, which is mostly just sand, clay, and little bits of straw. Great at performing thermal mass. So when you integrate these systems of insulation and mass together, very strategically designing a room or a wall or an entire thermal envelope of a house in conjunction with what your needs are for your space heating of bedroom versus kitchen versus living space and so on. That's where like your true comfort can be arrived at relatively easily from very simple building block materials like clay, sand, straw, timber, stone, and so on. But how to use thermal mass productively. And also window locations. That's where this, I should have had this one first.
Alright folks, so we're taking it up a notch here. This is, the insulation is a basic part of this, and then the thermal mass, and where we're coming to now is passive solar. Is that about the gist of it?
Yeah.
And it's really sort of, it's a complex, like the shifts in the weather, we're responding to the shifts in the weather, and we're trying to build a system that performs adequately. And it's really sort of the combination of these different concepts. And it's fundamental that you understand the difference between insulation and thermal mass. Materials, you have one material, you have this paper. It has a different thermal mass and insulation value than a straw bale. Radically different. So to sort of understand the thermal mass, this concept of holding on to energy, retaining energy, like almost like a battery.
Yeah, or like soil does, or like a sheet mulched garden holds moisture. You know, it's designing the forest garden house. So we want it to be self-regulating. That's where the passive strategy comes in. That's exactly what we're after. Straw clay, straw bale, whatever kind of format you design these strategies, we're simply we're choosing the deliberate interaction and relationship of materials to provide the yield of comfort. That's what it's all about. That's what it comes down to. So how to make that self-regulation of an internal environment for our finicky skin and body needs. You know, it's where, good thing we got these big things on top of our shoulders, because that's it's a hard concept, or it's a hard reality, and it's demanding to try to get there. But passive heating and cooling strategies. It's the window locations are a huge part of that. So, in the summertime, we got the sun kind of coming up right around here. We got this wonderful roof overhang, keeping some of that heat out. And it's a problem with my 200-plus-year-old houses. They don't do that. It's about 91 degrees upstairs in my house probably right now. A good roof overhang, strategically placed. The roof pitch is a big part of this. Again, the solar panel and installation as well. But your roof pitch, simply that's this angle that it's coming down on, and how far out. This is called a fascia and a soffit right here. That's just like, it's usually some version of a 90-degree angle, or finishing detail at the end of a roof where it overhangs. There's a lot of different purposes and functions to that, but for our needs right now, it's like how to work in conjunction with the window placement and to capture and prevent solar gain. And for me, I like things cooler rather than warmer. So this time of year is harder for me. I always, if I had my way, I'd have a whole bunch of unhappy clients because I would design all windows to just to avoid as much sunlight as possible. But in the winter, our sun angle changes, and on the horizon it's going to come down somewhere else. So we want a roof overhang to keep out summer sun, maximize winter sun. This chart, or this photo here does, okay, it's the winter, but this does not show the full picture of window placement. It's a three-dimensional thing. So the window height, if it's right here, that's, you kind of go up or down to make sure we capture that. I think that's pretty self-explanatory. There's this other aspect in a 14-inch or 18-inch wall system. You can go inside and outside with your window location. This is where it gets really kind of fun and funky. But normally the window is mostly to the exterior of a wall system. You can play with that if it's properly protected from moisture and snow buildup. You can kind of play with where that goes. And windows, as I alluded to before, is calling them the big evil hole in the wall. They're not very good at insulating. So they're horribly poor at insulating. Is really the thing. What we try to do is there's a strategy and a formula for trying to arrive at where that your solar gain and therefore your heat gain from a window placement outweighs its negative insulating capacities. So, does that make sense? You want more good heat or light to come in than what you're going to lose by it being a hole in the wall. We'll just put that not until we need it.
Is that going to vary based on sort of latitude? Or
Yeah.
So it's sort of ideal basis of where you are on the planet?
Yes, yeah. And the amount of daylight per per season. So a lot of this we've got to yet to see movable windows that kind of slide up or down with the season, but it's probably coming to that. There's some good geeks out there doing some pretty creative things, but you really kind of want to go with like your equinox dates or how much daylight you have at your latitude, September 21st and March 21st, and kind of make your numbers from there. And also adjust in if you're designing for yourself. Do I like a little cooler or a little warmer? Or do I have an occupation that's going to leave me arthritic in 20 years, and I'm going to, my body, is going to want a little bit more warmth for comfort down the line. Making these bigger personalized decisions of which way to sway your ideal location of a window. But really, what you're looking at is a window has poor insulating qualities to it. You want to maximize what you get from it in the form of heat and daylight, and minimize what you lose. But a window sill, 14-inch wall, for example, if your window is kind of to the exterior of that, you got like 12 inches plus or minus to the inside. That's just a perfect place for thermal mass. So like soapstone windowsills or any kind of stone. Wood is a wonderful structural material in that it's renewable and available locally. That's not much of a insulator or thermal mass producer, or doesn't yield much in the way of thermal mass gains. So it's a good. There's a lot of windowsills out there that are made of wood. It's a good, easy kind of piece of low-hanging fruit to eliminate wood windowsills in favor of something with good thermal mass capabilities. Especially if you're getting into food growing, because you've got 12 inches there, and it's kind of a perfect place for seedlings or even just for plants for air filtration and so on. You can work with windowsills as like your kind of like baseline thermal mass location. There's floors are next, and then walls would be right after that. But so that's a little bit on how thermal mass works in your space. So you want to trap insulation. You want your insulation to trap heat for.
I always sort of had the idea of looking at it like you're using the greenhouse effect, and you get that energy in there, and you're using like the thermal mass as a battery to store that energy. And you can overdo it at times. Like that's what you gotta worry about with too much glazing. If you have too much glazing and your battery overheats, it's going to overheat. You're going to make your house overheat. So you have to have cooling strategies or shading strategies.
Absolutely. Yeah, that's. I think I first learned about thermal mass here by all the 5-gallon buckets of water out in the greenhouses, and it's exactly what it was all about. Yeah.
Brian, it's like 10, 11.
Okay.
I don't know when you want to take a break.
Maybe that too. Want to take a now or
Yeah,
10 more
10
minutes?
break.
If I could say one more thing about this thermal mass too, like we're saying it could overheat and overheat the space, but it could also be cold, like an iceberg. Like if the thermal mass develops a negative capacity, it starts to work against you. So there's water is a brilliant example of thermal mass because you can bring it to the space how you like it, warm or cold. And then if you need to change the temperature, you change the temperature of the water. Or you remove that water. It's movable thermal mass.
And so, just quickly, southwest versus northeast, thermal mass strategies are drastically different. It's very predictable weather in the southwest. Hot, dry, cool nights, clear nights, kind of dreamy, especially from a builder's point of view. But so your strategies, just kind of looking at that, 32 to 45 degree average temperature throughout the year. That's significantly different. So 35 to 70 inches of rain, that's, you got hard up here. So just kind of think about your localized solutions. That's kind of what it comes down to. Is thermal mass. It's a simple concept in the West where you're looking for cool as much as heat, and it's a kind of linear function of sun up, sun down, warmth, dry, or warmth, cool, and dry, moist. But here it's not necessarily the case. So it requires a lot more design up front and forethought. So, yeah. All right, 10-minute break. That's fun. We're on the clock. We're going to start rambling about something. Be interested to meet that.
Brian, the north, south, east, west.
Yeah, and actually, I'm going to completely ignore that because we're going to get into it quite a bit with the site assessment.
Oh, okay.
Yeah. So, yeah, absolutely. And glazing, like window locations based on what the first kind of generation of passive heating buildings in this country in the 70s into the 80s are almost everyone I've seen or heard about is basically an overheated space. And just from thinking, we need 60% of this wall surface to be windows. Usually it's like in the south you want 26 to 32% glazing. That's a pretty good ratio. In the west, you want actually somewhat comparable to that. In the east, less, and in the north, drastically less. But if you can avoid the north is berming a house into the ground or partially into the ground on the north side is
you're building your house in
perfect strategy here.
We have a young couple in town that is doing that. They bury glass. And they put a little A-frame on top though because they need a little more space. And they really do a nice job.
Yeah, it's a good way to go.
It's not just like
some moisture issues you got to design for and something, but there's a million ways to do it.
I don't know the particulars of it,
that's how we've done
but I know they're doing it and they're really excited about it.
Yeah, I hang out down in the basement.
Yeah.
So
yeah,
cool.
I mean,
Get a couple of photos ready.
like comfort.
Oh, yeah, my basement and garage are cold all the way through the winter. Too nice.
Yeah.
Sleep in a tent last night?
Yeah.
Nice, right? Nice night.
Yeah, it was pretty good. Comfortable.
Yeah.
It was 10 was on more of a hill than I thought it was, so I was sliding down a bit, but
Yeah, it's
that was the only problem.
Beautiful weather though, camping out.
Yeah, great weather for that.
Do you think we should just let the camera keep going, or stop it and
Can
start
you
it
pause
over?
it? Is it obvious? Not mucking with it too much?
It looks obvious enough.
Straw,
Yeah, that
straw and mold.
it can be an issue. So back to every function is supported by many elements.
Okay.
So your structure, your insulation, your thermal mass, all these should have several elements throughout a building that provide that function. Now, your resiliency factor, this is pretty big, on what you're trying to avoid. So in a garden, you've got like disease and drought and so on, and you have many strategies to try to avoid. In a building, or in particular, in this case, a wall system, one of the biggest things that you need to mitigate against and design for the elimination of, or hopefully elimination of, is water in your wall. So when you're talking about that dew point, and the clay being a fantastic feature to having water be able to permeate through and air not being able to, that's what you're after. But in a true straw-baled wall, and this is different than a straw clay wall, you've got your plaster on both sides, and then you make the assumption that you've got 14 inches or 18, depending on how you orient your bale, of straw that you make this assumption that you moved the dew point to the interior or the exterior of that, and that you mitigated against moisture settling in that wall system, and which is never going to fully happen. So vapor will come in, and then a common strategy is to allow for the diffusion downward. If the dew point forms in the bale, for water to be able to drip down and export the building. So through just proper drainage. And it's a detailing fact. Actually, I'll show some pictures of that in a moment that are really good. But the true fact is that's only one strategy, because there's always, water's going to get everywhere. And no matter how well detailed and sealed the building is, you're going to have either water or vapor or air infiltration or pressure infiltration in ways that you can't predict over time, just through the natural compostability of some of the materials. So a lot of these last hundreds of years if maintained, but you have to, as a designer in a building, have to assume that people down the line are going to maintain less than ideal. You have to. Yeah. Even if it's not the case, then this is just one more strategy for proper resiliency in a wall system.
What type of longevity then with straw walls?
Well, so the verdict's out, because the oldest ones are like 120 years, and when maintained are fine. I should say the oldest known ones. People are probably building. Straw. Here's a trick. Straw clay has a longer history than straw bales, which are a mechanized, the product of a mechanized system, of a baling machine. So there's not a long history of that. There's a century or more, but it's, timber frames, there's plenty that are like 1,800 years old to like significantly older that have had some level of restoration. Natural wall, there's plenty of buildings throughout the Mideast that have been, infiltrated by UV radiation for centuries and are fine through proper maintenance. Cob, adobe, and stone, brick, or fire clay, all these types of things can have a very, very long history of longevity. So straw bale, it's just an interesting thing that as much as it's a natural building material, it's the result of a baling machine. So in that very particular instance, we got some that are like 110, 115 years old, 120 years old, in that range, that are still fine when maintained. But we can't yet give the multi-century longevity stamp of approval. So, yeah. Wood chip clay, straw clay, some of these other systems have been around a lot longer. But,
What about settling at the top of the roof, the top of the wall? Is that straw going to settle down? You're going to create an air pocket in there? Can you get an implosion of the...
I'll show a couple of construction details in a minute. I want to go over just a few design features that I think will be applicable to everybody, and then I can just show a couple of pictures on construction details later. So, good shoes, that's the foundation. So a good hat and a good pair of boots is kind of like the general, long ago established buzz phrase for design principles. So a really good foundation to make sure things are up off the ground, they're well sealed, and you're either using the geothermal benefits of the Earth's core temperature or eliminating it and having a barrier between the Earth, depending on your strategy. But a good hat, you want a really big roof that both protects the walls and is part of your passive solar heating and cooling strategy that we talked about. Those are the kind of basics. And then we're getting into like the good coat bit, and all that's really kind of, I think we've talked about it a little bit through the air, started with the air sealing, but then the next kind of evolution, and this is then this book right here. Some friends in Vermont just put this out. This is the most up-to-date guide. It's a really exciting new production. Big textbook, and there's like a DVD package and stuff at the end. It's got all sorts of good stuff. These folks have been working, working with blower door tests and high performance, extreme high performance energy efficiency in natural buildings. And this is like this pretty exciting merger of, green building and the natural building movement. And green building, I mean, kind of tends to focus on energy efficiency and type houses, fancy windows, high-tech strategies, and so on. There's a lot of role for those types of things, for sure. I think my approach is pretty firmly rooted in localized materials, healthy materials, low-processed materials, age-old traditions and strategies, and then kind of integrating in some building science and systems. So heating systems and photovoltaics and heat and ventilation recovery systems, and things that definitely have a role in the modern natural house. But for years it's kind of like this, no, we do it this way, no, we do it this way, we want breathable walls, we want tight houses, and it was kind of a bit of a battle. And I would definitely just kind of like recently, through a lot of this stuff right here, been getting pretty excited about designing like R50 wall systems out of straw bales and R90 roofs that are, or R86 roof systems that are using almost all natural materials and pretty simple strategies that, 2,000 square foot houses being designed to burn just over half a quart of wood per year. It's pretty great.
And so now there are also sort of, the Venmar type products that are designed to make for air exchange now that we've made our houses so tight. Could it be that we've gone a little bit too far?
Yeah.
That we might...
So last winter, there was 17 people hospitalized in Germany. There's real brief kind of connected with this. There's a lot of house certification programs out there, and there's the most popular worldwide, the fastest growing one worldwide right now is called the Passive House, and it's a set of standards that measures how many air changes per hour a building envelope goes through. And what that means is a full 100% transfer of interior air to the exterior, so a full filtration of air. In this country, even right now, like 4 air changes per hour is kind of seen as like a silver standard. It's not like fantastic, but people are still calling that pretty good. In kind of conventional circles, people using spray foams and things. And this passive house movement started in Germany, and they've got to achieve that certification. It can be a 0.6 air change per hour, which is very, very low. And there's some being designed and built that are like 0.15. That's like the latest goal that everyone's kind of like shooting to achieve. So, and in Germany, there's like 30,000+ certified passive houses. In the United States, there's 11 so far. We just designed one that couldn't get funding to be built in Plymouth this year, and so it's not a cheap build, but it's a pretty high standard, and it gets down to window detailing and tons of architectural details, but it does not even touch on material selection or indoor air quality, health of occupant at all. It doesn't even look at that, doesn't even register. So 17 people in Germany last year were hospitalized for the power went out, and their automated HRV systems shut down, so no outside air could get pumped in, and 17 people were critically ill in like a 1-day period of being without power. So it's this real discrepancy on like that forest garden house, like self-regulating ecosystem, versus can't be without power for 24 hours if you get hospitalized. The energy efficiency on those particular houses is unbelievably high, but at what cost? So it's philosophical differences on building strategies and solutions. But the merger, natural building, healthy materials, and getting some airflow and air quality issues being integrated in. There's another living building, is that right? Mm-hmm. Living Building Institute standards. Yeah, that kind of incorporates community processes, material selection, indoor occupancy health, and I think actually they're the ones who pioneered the 100-mile home challenge. So that's a standard that's Canadian-based, I think, and gaining relevancy in the United States. A pretty exciting standard. So The good coat, yeah, the good buttons. This is the good stuff. So the book going around kind of gets into the air sealing strategies and details for straw bale houses and straw clay houses and wood chip clay houses.
I've got a question about good coat vapor permeability. In the hiking world, you have Gore-Tex that lets vapor out one way and doesn't let it in the other.
Does it? It just says it on the tag, man. I still sweat in that stuff.
Just wondering if there was a building material that had kind of similar features that would be, just use it on a panel, like one little vapor lock at the top where you'd be letting stuff out. I don't know.
Well, that's what the Tyvek's supposed to do.
Yeah, but it will trap condensed liquid moisture. Then that it can't allow that out. I kind of feel like clay is about as close as we can get to it.
But that's two ways though. That's coming both ways, right?
Yeah. So then integrating the benefits and inherent and intrinsic elements of what clay does as a functionally with air sealing strategies on the inside and the outside.
Okay.
So yeah, and that's exactly what this stuff kind of gets into.
I think where the basic dichotomy is that you're trying to build more or less spaceships, that have air control, and what the opposition to that is building an Earthship that has a natural regulation of the air control. So there's this one very mechanical sort of constructed methodology, and the other one allows the natural materials to perform.
I hadn't heard that, the spaceship, Earthship. That's good.
I'll write this down.
That's good stuff. Is the pointer? Okay, good. So I can use this to point. So this is that toe-up detail I was talking about before, where if moisture comes in and gets through your wall system, it kind of comes down. It's a 2x4 and a 2x4, and in this case, that piece of rigid foam that acts as both a good insulator and we were talking about that before. But this right here is these are plaster. Actually, this is better. All right, I'm going to come back to this one because this was that question at the top of the wall. But.
The full air exchange thing that you were talking about. Mm-hmm. So for a straw bale house, what would the average be?
So a lot of the newer innovative ideas that are getting more high tech on the air sealing in the straw bale homes, like 0.8, 0.10, without getting too mechanical or without getting too expensive on windows. Windows are the kicker to it. Right now, like the average house, the passive house standards to achieve that 0.6, there's like a $40,000 to $50,000 window package for like a moderate, like 1,200 square foot house or something. It's a lot of money. So, so without going to that level of windows, of crazy high quality windows, and allowing it to not be quite so tight, like 0.8 is pretty achievable. Yeah, through just natural materials.
So the folks in Germany who got sick, they were at what level of lack of it? I mean, what level of air exchange do you need to have in order for it to not be an unhealthy situation?
Somewhere in the 2, like 2.0, not even a 0.2. So yeah, somewhere in there is generally seen as like being kind of, and actually even that's pretty tight. So 0.4 is, 4.0 is kind of like a common goal in this area. There's a lot of programs and initiatives that are federally funded and state funded right now that are trying to move towards energy efficiency in older homes, and like 4 air changes per hour is like the goal, and it's not all that great, but it's way better than 12 or whatever.
It certainly depends on what the air quality is initially to it.
Right,
If your house is built out of toxic materials, then you want more exterior air exchange.
Yeah.
Or if there's a high dust content in the building, you might be seeking more of a filtration capacity, air exchange capacity. But some of it is this balance between insulation and retaining heat or cool within the building, because every time these air gets exchanged, you have to compensate for that with the heating or cooling mechanism of the building. So it's this balancing act. It really, I think the danger is that these very high-tech buildings have a lot of toxicity. So when people get trapped in them, this becomes a place of a toxic environment.
Mm-hmm. Yeah, that's there's different ways in which materials are unhealthy, and it really does play at the heart of all of it. So there's some of the, I think now more understood and recognized ones are off-gassing of things like paints and finishes and so on. The lead paint thing 30 years ago, 40 years ago, that was probably one of the first nationwide campaigns, I guess, to understand indoor air quality, but or in some major way. But that's
We'll be eating in a little while.
okay. All right. So finishes and chemically arrived at solutions, whether paint or finishes and so on, are a pretty big indicator now. So that it's pretty easy to avoid. But unfortunately, like a lot of straight up materials that are spec'd out by architects and are used in buildings can be unhealthy on their own. Like structural insulated panels will off-gas for 30,000 years or something like that. There's like all these like urethane-based foams in there that, in the oriented strand board and even plywoods have formaldehyde and glue just embedded into them. But in a way, those products are pretty interesting. They're modular and easy to work with and very predictable. And they're like recycled wood chips glued together. And glue is the problem. So a lot of these things have these elements to them. And in a tight house, you trap it in, and you're kind of set up for danger. Electromagnetic fields, and there's other dangers. Like, there's a lot of research being done now on the trapping of different, I don't even know the terminology for it all, but different waves from remote controls to batteries to wireless signals and so on, and just we're just trapping ourselves in when we go super, super tight. So, but it's kind of achievable, and I've been excited about using clay embedded into a wall system where that helps mitigate moisture. And a lot of the natural occurring toxic problems are in the form of mold or mildew, and a lot of that can be mitigated through moisture management, which can be done with clay. So it's predominant way to deal with these things is by adding as much clay as you can into your wall system. And one other just real brief thing before getting into that, but on the issue of clay is even if you do like a pretty standardized approach of say 12-inch straw clay wall system all the way around, a lot of times you'll put like a lot more straw in the north side where you want more insulation and a whole bunch more clay in your mix, and kind of temper your mix with more clay in the south where you want the thermal mass capabilities, and bathrooms and kitchens and places where people shower, cook, or lots of people get together and breathe in a living room or something. You can manage all that moisture by how you actually make your wall, by just knowing what the use is going to be. So it's a good strategy is just manage clay content based on what the use is going to be. So so this is that air sealing. This is the good button feature. This is a really common approach these days on a straw bale system. This could be straw clay, it could be something different, but we've got a timber frame. This is the inside of the building here, and this is a finished coat of plaster and a rough coat of plaster. And this right here is called homosoap or soundboard. People have heard of that. It can be a variety of different things, but it's a very common material. You can get it at a building supply store. You can use felt paper. You can use Tyvek if you want there. I've yet to see that done. But the level of detailing that's happening here, there's a acoustical sealant, which is just applied with a caulking gun. It comes in a tube. It's kind of a nasty material, but it has a good benefit. It's not an unhealthy off-gasser, but it's a very highly processed material. But so you've got a timber frame, and all your plaster kind of comes up and tucks in this little notch carved out of the frame. This homosote goes up to the outside, and then your veil comes through. So you've got continuous plaster here, but clay, high clay content here, and timber. And what's one of the biggest things going on in timber? It's anybody got a wood floor in their house?
Expansion, contraction.
Yeah,
How do you do that?
Yeah, organic materials. What's that?
How do you deal with the clay doesn't expand and contract, but the timber's going to? So how do you?
Well, the clay actually will on a molecular level. It will take on and release moisture, and it will move. It's not as visual, but in your plaster, the cracking will definitely happen. So what we do here, right here where this intersection is, so this may be 2 inches from maybe 4 or something like that, some level of overlap. So this plaster comes up and over this homosote, and this gets fastened in. That homosote comes like the full length of the timber. And this is at like all the junctions between your insulating system and timber system, structure, skeleton. You put that homosote up and seal it, and this is fastened, like the screws of this go like right through where this bead of caulking goes, and not even a screw hole goes through where it's not going to get sealed, ideally. But that expansion contraction joint of the plaster to timber, which is known to be problematic, can get dealt with by just putting that homosote, which acts as a complete air barrier. It won't ever be altered or changed unless somebody gets into the wall and does something with it. So you've got, if this is an 8-inch timber, you've got, say, a 12 to 14-inch strip of homosote that runs up that, and the plaster seal just happens on the inside and the outside of that. And at the exterior, there's no timber framework at all, so it's just one big layer of skin of plaster to the outside. So the way that gets dealt with here at a window is very similar. So these are all different strategies. There's all these levels of preventing. This is like that resiliency factor. How many ways can you stop air from getting through a space? And that's kind of what this comes down to, is resiliency and redundancy of building systems. This one's pretty basic. The top one. All right, this one's important, but I want to go to this is one way to deal with what was somebody asked about the top of the wheel and the wall and settling.
Yeah.
So straw will do that. There's 2 ways. There's different types of straw bale systems. 2 major types. There's what's called load bearing and non-load bearing. So in our climate, with the amount of snow and wind pressure and so on that happens, almost always use non-load bearing straw bale walls, which means there's some sort of framework outside of the bales, like a timber frame or some framing system, and then the bales are just being thought of as your insulation. In a load-bearing wall, straw bale wall, like in the Midwest, they actually have to put big plates up on top, like timber plates, and then come along some straps, like every 2 feet, and compress it down, like pre-compress it. You can get like a foot out of an 8-foot wall of compression, where you just tighten it as much as possible. And then you go through the chainsaw and square the bales back up and everything, or weed whacker or something. You flatten your walls again, and they're pre-compressed. So in a straw bale wall, what we're doing now, which I think is the best, it's so basic, but for some reason it hadn't been done for a long time. Actually, I don't think that picture shows it accurately. Well, that's good. Your wall system, so you've got a timber frame. I say timber frame, it can be other things, but big timber network in here that's holding up, like throughout the whole perimeter of the house, and holding everything up. Then you've got, see, it's a little tricky to see it, but here's your straw bale, and in this case it's shown as cellulose, and up here your roof insulation. Your roof is where about 65 or 70% of your heat will be lost through, with appropriate window design. Otherwise it's like windows will be a high percentage of heat loss. But your roof is actually a more important drastically more important place to insulate well in your walls. So in this case, this is all just blown-in insulation. This kind of demonstrates it. It's tricky to see, but what we've been doing is putting straw bales up to a certain height and just leaving a huge open cavity right here. This is by far the biggest issue that building inspectors will criticize on a straw bale. Again, this is shown in cellulose, but on a straw bale wall system, there's every other kind of house has this big separate feature of the walls being very distinctly separate from the roof system, both in terms of structure and insulation. And by putting the structure to the inside and the timber frame and all your loads getting taken there, being the opportunity to merge your roof insulation to your wall insulation by just using a dense packed cellulose that just spills over into the top of your straw bale is the simplest, most elegant, and most confrontational approach to insulating. But
is that because the inspectors want a fire stop?
Yeah, that's exactly what it is. And it's the biggest. So the roof is supposed to be thought of as its like separate entity that can be replaceable too.
Especially with straw, I would think that would be like a chimney.
Exactly. Yeah, because that's your
fire chimney.
The way pressure and air works in the wall is to rise up through that.
So how do you deal with that? How do you convince
There's nothing there that can catch fire.
Huh?
There's nothing there that can catch fire.
Straw's fire flammable. We'll get their argument.
With only when there's air, and with that air sealing all the way through. And only if that was broken can air
but
get in.
Have you been able to get building codes changed to acknowledge that?
There's a wonderful group of people working on that, and I am not about to put my energy into it at this point. But yeah, there's a lot of people. There's the Developmental Center for Appropriate Technology, centered in Tucson, Arizona. And they have been at this for 20 plus years, getting natural building to acceptance and code compliance. On a regular basis, they've been changing state codes. Yeah, so it's been great. They've been doing a lot. They don't do anything out here for us East Coasters, but luckily, most of the folks out here will just be like, oh, they're doing it in Oregon, so we can, we'll amend it or sign off or give approval and see and inspect out and thought through. So
I know my own local building inspector is so by the book. He would have a very, very difficult time accepting that.
So the community of natural builders that is out there right now is pretty great on sharing information. DCAT.org is the website, Developmental Center for Appropriate Technology.
I think they've got some stuff through NFPA with this already.
I think so too. Yeah. The whole code thing is great too. I mean, it's got a bad rap, but it's there for a reason.
Before you move on that, I'll leave you with this image either way, but what I thought I heard you saying was when you have the straw bale rack outside of the frame and it comes up to the roof, you have this opportunity to bring the cellulose cavity and have the two merge for really creating a blanket, a seamless blanket.
Yeah.
And when you're forced to make a break in that structurally, you've got a separate wall component, a separate ceiling roof component, then you have the opportunity for thermal bridging, air infiltration, all these problems.
Yeah.
So it's changing the way we think about construction because that break doesn't help it structurally.
Exactly.
Okay.
Yeah.
So I make sure I understood the way you were describing it.
Yeah, back to the thermal bridging. That's a whole thing. Didn't use the phrase again, but it's really kind of what this all comes down to is minimizing transitions between systems, like in this case a wall and a roof system, and because those junctions are very, very, very often where bad thermal bridging happens, and those transitions are also places where problems arise. So like the field would be, like this would be called the field, like the big kind of one thing, where it's all the same, very, very simple, like a big wall. I mean, that's a nice, beautiful painted one, but someone got to paint that. Originally, they put on like one big edge, got all the edges, that's where all the time happens, and then with the roller, you take 4 minutes and do the whole big thing you see. With a building, it's kind of the same way, like your fields are pretty simple, and all your edges and transitions, kind of like, back to the garden theme again. That's where all the complexity happens at your edging, and that's exactly what's going on here in the building as well. So, yeah, that's The etching's good in a garden. It's not so good. The building, it's where you're just trying to like minimize. So right here you got roof insulation. Right here, there's that connection. It just spills right in and it's done. So if this settles 3 inches over time, this settles with it.
Okay, that roof insulation you're talking about.
Yeah.
What is that?
In this case, it's cellulose.
Okay.
I'd almost always use cellulose in a roof insulation if possible. There are people who have done strop, and there's people who have done foam. There's ways, if there's ever an appropriate place for structural panels, it's in a roof, not a wall, but in a roof you can do it just because it's really quick. And if you're in a wet climate, you can put your straw bale walls up and then throw your panels on the next day with a crane. And 1 day later, you've got protection. Otherwise, it'd take a week or more to build out a roof. But yeah. So, all right. So those are some of the construction details. So air sealing details. These are all big. These are all part of the natural building arsenal of tools now. This is sealant that goes in. It's, I think, negative 400 degrees to fire temperatures or something. It will stay elastic through all of that, so it will always move and bend with features around it, which, you know, we ask a lot of our buildings, but negative 400 is probably not in our near future. So, so lots of detailing around and then testing on how to get extreme. Yeah, we'll probably skip over this. But again, this is the plaster edges. So just quickly to read through, windows and top of wall details are where most of the transitions are where the problems happen. And the way to test, you can see it right here. Anywhere where you've got less red, that's your problem joint. So
I think while you have that up, it's worth, aside from natural building, just from a permaculture perspective, where we're focused on energy conservation and using resources well, if you have existing structures that you haven't done an energy audit on, they haven't done blower door tests, and you haven't had someone come in with a thermal imaging camera, those are all good steps because there's an opportunity for you to add more insulation, add dense packed cellulose, or do some air sealing of a place where wind is blown through. We're not getting air exchange, we're getting too much. But that kind of information can be really helpful. Has anybody done one on their place?
I haven't actually done one, but we have the equipment, and I work with somebody that does one.
Yep.
And they do remediation at the same time. So
great.
Yeah.
Our house is almost ready
to do one.
We knew we needed to do all the work that we did last time. We replaced our skylights with sky tubes.
Yeah.
After 20 years, one started leaking, and the newer ones that we put down in the front were leaking within 2 years. But as I said, we're like really trying to figure out how to tighten it up. And we have one more wall, but we're going to do a test this summer. Or actually, I think we were waiting until the weather's turning cold because I think that's the more optimum time to do it.
I just think, as Brian was showing that, I think it's important to know that you can go through. I mean, we've gone through 3 blower door tests.
In your house?
Just our house. Yeah.
What test?
Blower door, where they actually remove the air so you can see air infiltration. So what Brian's showing is, during the construction process, they can actually test and see how well the air fins and the plaster and everything is doing the job intended by seeing if they're getting air infiltration in places. And there's still a chance at that point, Brian, to address some of those issues, right?
Absolutely, yeah. And there's having that information of where the problematic spots are, it just tools you with the information needed to make good design strategies and renovation strategies. And I think it's the movement of, not everyone's going to rebuild, not everybody should be building new homes and really working with what you got, that's, so it could be a good case of the problem is the solution. If you know where your trouble spots are, and you know you need to add thermal mass, well, there you go. That's like how to work in thermal mass, how to work in healthier materials into what you've got based on where you know your trouble spots are. So it's usually anywhere from $200 to $600, depending on the level of testing you're going to do. And there's a lot of programs out that will do it for free these days. So I don't know all the websites. Any Plymouth residents or Berlin residents?
Yeah.
But yeah, so information is out there on how to get that information, because we all live in houses, so you might as well know it really well.
I already know my house leaks the Pacific.
Yeah.
You can, with a candle going like this.
Oh yeah. If I put a candle up against my windows, it would blow out.
You can feel your hair blowing.
Yeah, the window shades will move on a windy day.
Brian, what's your time constraint today? I know they're blowing the horn for lunch, and we don't have to go down right away, but...
I'm on kid duty by 1 o'clock for the day.
So we definitely want to make sure
I'm on
you
your
get a
duty.
chance to run through some photos and answer questions. We can get out of it.
Yeah, well, I was just going to put that up as just like the final one, and then go right to questions. But that's, that's what it's about.
Farm raising.
People working together. So it's definitely about reskilling, not de-skilling, working with natural materials. Because I think for a long time there was a thought process that it's really simple and anybody can do it, which the anybody can do it part is I strongly advocate, and everybody should be involved in it, but there's a lot of technical information and strategies and so on, how to conduct a natural building site and the space requirements for dealing with having lots of people, incorporating in as much volunteer labor as possible. The big kind of the difficult aspect of making natural building more viable for more people and more projects and work sites is that it's very labor intensive. We're replacing mechanized labor and energy with human labor. We're going back to a step where there's more people, more hands, more caloric energy involved rather than mechanical energy. And it's huge. It's a very big step because there are very efficient machines and processes that can be done off-site and ignored. And when we come back to being involved and putting a lot of labor into something, that's major. So luckily, it's a whole hell of a lot of fun, more often than not. But it really does require working with people. It's a human dynamic. And a job site of this type of magnitude can be, to do, say, a timber frame raising and a wall system, and then a couple of coats of plaster. That can easily be 4 or 5 months. Not continuous, but a 4 or 5 month, a full building season push with, 10 to 15 days of 20 or more people working together. If you like that, and it's great. And there's some people who might not be as attracted to it. So it's just important really to know that you're putting human labor and you're valuing it and exploiting it at the same time. So you're putting it out and you get your friends and your family or whatever kind of group of people together. It's what it's doing. So it's really important to know that that's what you're after. So setting up a site, setting up efficient material flows and so on is a huge part of it. But there's great days. Up in Rumney is the project that ended up having borax in the walls the year after this. That was the first big frame raising that I did. And yeah, I had done a lot of other people's. It was the first one I got to conduct. There's nothing like 75 people working together. It's unbelievably awesome and rewarding. So just leave that up as we do questions until it shuts itself down. But just know that that's a big part of what's happening is, people working together to achieve whatever it is your goals are. So, yeah. Mm-hmm. All right. So questions and how it.
This is kind of like off subject, but it's more concern in my neighborhood down in the Nadnuk region. We've been getting really flooded because our main town Keene is located in the basin, and we've had serious floods. Like 2 weeks ago, people were kayaking on the roads, and this is like the second or third major flood in 5 years. So, I'm not sure whether the town government will ever make some sort of decision about relocating houses to the surrounding hills, which I don't know if that's a better idea or not. I mean, in retrospect, all these beautiful fertile valleys would have made great places to grow food, and you know, people wouldn't be dealing with water in their basements if they were above the water line. But my question is sort of, is there any bigger, broad scale, you know, piece to the natural building field of study that addresses the long-term, how do we deal with cities that are like New Orleans, and you know, is there any definitive kind of...
Two things come to mind. The first is you're already taking a class in that bigger scale, permaculture.
Right.
I really think that I see natural building as being a component of the overall permaculture philosophy. Mm-hmm. It's like the structures and infrastructure piece of permaculture. Mm-hmm. But you know, 2 years ago or so, somebody came here and was talking about relief work being done in Haiti, that there's a large team, like an international team of hundreds of people, the natural builders that have been converging on Haiti to, you know, add input and work towards solutions on the cleanup and rebuilding effort. And I think there's a lot of opportunity for that, and certainly on a more global scale, there's more or less any kind of permaculture movement, I think, is going to have an element of natural building to it, that people are involved in. So, yeah, I would just say the greater permaculture movement is at the heart of it. And, this is just one component of it. So. But, yeah, as far as relief work, large-scale town and urban planning, absolutely. I mean, this being a piece of that permaculture philosophy, hopefully will take root.
There's like people who do relief projects all over the place, like in Haiti and other places, like in New Orleans, etc. Building new houses for people that are made out of cob, etc. Like, if any of you have looked into earthships before, you probably know what earthships are, right?
A bit, yeah.
From like the headquarters in Tasman, Mexico.
Mm-hmm.
But like that organization, they build like small earthships for people who have gone through disasters like that, and they do relief projects. So it could be something like that, you know. If that's what you're talking about, relocating houses that are in flooded locations.
I know just this talk was more house design on the exterior a little bit, but then you also went into the zipper and the belt, you know, the interior part. Because one of the things I'm always like thinking about, especially in winter, is, you know, the heat exchange between all that hot air trapped in the roof space, the attic space, getting it back down underneath. And is that a kind of viable? I mean, does this kind of lend itself to that kind of stuff as well too?
Sure. Yeah.
It just seems to me that sometimes it's like there's that effort to just seal off that roof part and not, you know, just kind of use it as a cap, as opposed to using it as a heat regurgitation type thing.
Mm-hmm.
Yeah. The problem with a hot attic space is it's only hot when you don't want it to be. You know, it's not like you don't have access to it in January when you want it. But there's the heat vent recovery systems, or heat and ventilation recovery systems, HRVs, that are really that's the mechanical method of doing that. So from like a dryer in a kitchen, in a bathroom after a shower, like all these places where heat in some form is generated before that air is, as Josh was talking about, before that's kind of like pumped out and other air pumped back in. There's heat exchangers in there that capture up to like 97%, which is really astounding. Right. 97% of the heat before it's pushed out is held and captured and used to heat the air being pumped in. So you have 97% recovery.
So that's not necessarily the building, that's more along the interior part of it, the processing of the air.
That's a mechanical and active strategy for it. There are passive strategies for interior air circulation,
right?
And through trom wall design, adding attached greenhouses. There's a lot of ways to passively heat small spaces during daylight and pump that heat in evening hours. Yeah, there's a fair amount. There'd be a big topic, but there's a lot of passive solar heating strategies and how to attach that for space heating. And it really comes back to thinking of house as an ecosystem of microclimates. Like really kind of getting around that concept of the whole house doesn't have to be treated the same way, or it's breaking it down into smaller spaces. Yeah, and then you can size your alternative heating system accordingly.
Ultimately, I think it does bear into that microclimate and utilizing, abundance or scarcity where you see fit. In this case, if the attic is not a usable space, then I would guess we would aim to do through design is prevent it from heating up in the first place. Like that would be the primary objective, is to not have a hot attic that's not a usable space in the wintertime. So you would aim to insulate that barrier, that cavity, the floor system of your attic, so that the heat never really builds up in that space that's not being used. That would be the primary. Yeah. That would be the preventative measure. And then by accomplishing that, then we would not have to use an active system to recirculate.
Okay, that makes more sense.
Yeah, my own house, when I went up to put insulation in the attic a few years ago, tore up the floorboards and found 8 inches of corn cobs in the floors.
Wow.
Colonial era insulation.
Yeah.
So I had to remove about 30 contractor bags of corn cobs, and then I put down 8 inches of insulation into the floor, and then 8 inches on top of that. The next winter, we don't have any heat on the second floor of the house. There's only heat on the first floor. The second floor temperature went up 5 degrees without changing the thermostat downstairs. Mm-hmm. And previously, when it snowed, the roof would melt snow off within a couple of days. Yeah. It doesn't go anywhere now.
And snow
massive difference.
Yeah.
Absolutely massive difference.
Have you had any experience with the roofs that are soil plants?
Yeah, so that's funny you say that, because I was going to say what you pointed out, I really did focus on like home design and elements of that, because it's kind of more complicated than everything else. There's so many aspects of natural building that are applicable, like from bread ovens and greenhouses and living rooms and so on. There's kind of just touched on some of the more complex stuff. So yeah, definitely living rooms are a great way to go, and incorporate most of the same principles in, and you get right down to like your products and yields pretty easily with that one. It's really just an extension of the
Have you had any
space.
experience with that?
Yeah. Done a few of them.
Okay.
And yeah, actually, we just did one in Plymouth. Actually, you guys ended up doing the finishing work on it, but at the college, as educational project, we ran a course last fall that was to build a shed that had a wood roof on it.
It's on High Street.
Yeah, it's right downtown.
How big of a shed?
Well, the roof itself is only like 5 by 10.
Something like that.
Yeah. The shed's a lot bigger than that. Just
You
one of
did
the
put like a
overhangs.
membrane, like a impermeable, like
Pond liner.
a liner, a pond liner.
So you just want to make sure you have enough structure underneath, and to support the weight. You just plan on not just the weight of the soil and vegetation that grows, but then adding to it like the snow and the ice buildup, because it tends to be a flatter roof. You're going to have a lot less pitch, so enough to drain some moisture, but you're going to end up with like a porch up there. So design for that load, and then design several layers of keeping moisture from getting into your structure. So like a pond liner, good aerated soil is going to be a big part of that, and then drainage, to make sure that the water in the form of snow or rainfall that does get there has a place to seep down and get off and not get trapped.
And you said it had to be a flat roof?
Not flat, but flatter. So, 6 pitch or 9 pitch or something in this range is pretty common. Like ideally it's like a 2 or a 3 pitch, something like that. Yeah. Less if you can. I mean, the 1/4 inch per 4 feet is what water requires to run, so as close to that as you dare get. But you do want to have, some velocity added to the
Kind
water.
of opposite the idea with the pitch out of roof to get the snow off.
Snow's not going to run off.
Yeah.
Snow won't come off.
Yeah. So it's just, thinking of it a garden, you don't want to design it in a way that...
Well, why not just
you need some strong-rooted plants to put up with all that slope and water pushing snow. Well, it would probably be dormant at that time. Yeah. But so, you want to just incorporate that in. And that's another whole topic that you could have gotten into, is like how to integrate a building as part of your landscape. It touched on, you know, the food growing, processing, storing, and so on. There's a lot, yeah. But the idea of using your building as part of your gardening strategy is a whole other element, and that kind of fits in there.
So why don't people build greenhouses on their roofs instead of attics? Because like I know lots of people with attics that they just don't use, and they're either not insulated or they do use them, but they use them for living space, or and it just gets too hot up there to live in there sometimes, or etc. Like why not just instead of having regular roofs, have a greenhouse on your roof? Because like you're talking about trying to figure out what to do with that heat. It's like, well, what, you know, how to get rid of it, how to keep it there. It's like,
Make sure it goes in your design.
Yeah.
All right. Well, I think we should close and head out to lunch. Yeah. Thank you very much for Bryan.